state of Hawaii and the country of the United States of America. We're glad to have all this international representation from all corners of the earth, and we expect to learn the latest update on what's happening in this area, the controversial area of cold fusion, or whatever people prefer to call it. Many people, as you know, helped organize this meeting, and we are very much indebted to them. And most of you know who they are. EPRI, we don't do most of the logistics of this meeting. And Linda Nelson is here. I'd like to introduce her to have her speak to you briefly about some housekeeping items and things that you might have forgotten about. Linda?
Good morning. Glad to see you all here today. I just want to
lights on stage, for instance.
Easily. We do have all the meeting sessions posted on the notice pages outside. If the wind isn't worked over 2 minutes. We will be signing all the meeting rooms to try and make it simple. The parallel sessions are going to be just next door, and again, they will all be signposted to make it simple for you. The luncheon today was originally scheduled to be outside on the Sunset Terrace. However, we just made the decision to bring it indoors due to the adverse weather conditions. Very typical for Maui, I'm told. It will be in the Maui Suites, which is just directly across the hall there. Just wanted to mention the luau tomorrow evening. All attendees are registered for that automatically. However, if we do have any guests that would like to attend the luau, we are asking an additional fee of $30 for that, which just helps to cover some of the costs. I think it will be a very good evening. Typical Hawaiian entertainment, wonderful food, I'm told. So we hope to see you all there. Just to have one other thing to mention. Sure, we would like to remember this meeting by having the official T-shirt. I'm sure you will agree it's very special. Those will be on sale as from this morning at the morning break. They will be on sale all week. Also, the official poster. So you will not forget this meeting. Again, the prices will be posted up on the board. All my team will be too pleased to help you on that. I just wish to say I hope you have a good meeting. I am here to try and make things run smoothly for you.
There's a temptation to launch into global discussions about the impact of the change of energy from oil, coal, and nuclear to cold fusion, and to restrict ourselves to what can we believe about phenomena we're talking about that we have already seen evidence of. We decided, because we couldn't afford it, to spend $40,000 to fully videotape all of these sessions. However, there are individuals, as you'll probably notice around the room, who are privately videotaping these sessions. What I would ask of the private people who are doing that to honor the speaker's request, whether he wishes to the tape, and if they decide that they would not, any speaker who wishes not to be so taped or recorded to honor their wishes. There are regarding proceedings, peer-reviewed, and then later in 1994, a subset of papers that are in fact passing a peer review will come out as a single volume as part of the ANS Fusion Technology Journal. At the speaker's breakfast every morning, I'd like to have all speakers. I only got half of my speakers this morning at the speaker's breakfast, so if you're speaking on a given day, show up and across the hall in this number 3 Maui room, and so we can have find out who's all here, because some of our speakers, one of them had a heart attack and won't be here tomorrow, underlung. And so every now and then we have changes in the agenda. I'd like to be aware of that in the morning so we can make the announcements. And this morning we have one thing to change in our agenda at the end of this morning's session. Kazuaki Matsui, the director of the R&D Center for the New Hydrogen Energy Project in Japan, will have a 10-minute presentation just prior to lunch. So don't run off right after the last speaker, because that's a very significant announcement. Any questions for If not, I'll introduce Michael Kubrick, who will share this section, and also the speakers. Also, Dr. Alan Miller will be assisting him to keep people on time. As you know, we're trying, I've only used 6.5 minutes. Hopefully, I won't have thrown the schedule into too bad a situation. Anyway, if any of you are happy with what's happening, I'd like to hear how happy you are. And if you're unhappy about anything, be sure and tell Linda Nelson. And she'll tell me indirectly. Thank you very much. Bye.
Well, I'd like to add my voice of welcome to that of Tom Hasson's. Welcome to you all. And hope we have a successful and cheerful conference. And have the distinct pleasure of introducing the unintroducible Martin Fleischmann to present the first paper in this morning's calorimetry session. Calorimetry of the PD D2O system, the search for simplicity and accuracy. Right.
That's costly. No, it's no problem. Thank you for the introduction. When Mike asked me to give this paper, I think it would be better if I lower this a little. How's that? Is that okay? Okay. I don't know whether there was really anything new I could say about this subject. So I thought that I would perhaps cover some of the points which have not been clear in the literature so far. We have never fully discussed why we launched ourselves on the subject, nor indeed why we adopt the particular approach which we have adopted. So I will try and cover that in the first part of this presentation. Well, as you all know, it is widely believed and known that we are interested in inserting neutrons into the palladium lattice and to increase the electrochemical potential of the species, the activity of the species in the lattice, which are neutrons, which are one I'll come back to. By applying a difference in galvanic potential.
Martin?
Yes?
Can you get it over here?
Yeah. It was better before.
Move it back.
Yes.
Okay. How's that? To increase the chemical potential of the species, the electrochemical potential of the species in the lattice by applying the galvanic potential difference between the membrane and the solution. And this is widely believed that this is the reason why we started this project, but this is not actually correct. The reason we started this was that because we were aware of some very important experiments carried out in 1928 by Alfred Cohen. Incidentally, it's Cohen, C-O-E-H-N, not Cohen, as presented. Everybody always wants to call him Alfred Cohen, but it's actually Alfred Cohen. What Alfred Cohen did, to summarize this, his experiment, was to deposit, at that time, of course, Cohen was not, so he deposited hydrogen ions into the wire, and he applied a potential difference to the wire. And he found that these hydrogen ions migrate in the lattice with a velocity which is given by the diffusion coefficient multiplied by the Nernst Einstein factor. Now that's, of course, was a very significant experiment because it showed that by applying the difference in galvanic potential along the wire, you could create neutrons, protons, and neutrons at an extremely high chemical potential. And this is the reason which prompted us to do this experiment. But of course, the most economical way in which we could apply a galvanic potential difference was not in the wire. If you think about it, it's quite hard to get a very high potential difference in wire. Although in principle, you could achieve something like 10 kilovolts per centimeter theoretically. So we decided to be more modest and do it at the electrode solution interface. Well, of course, what we were looking for originally were some signatures of the process. And if we now look at this in hindsight, because we're looking for trickle neutrons, Roger looked for radiography, charge particles, all this has not been done in Unit 4. We did actually look for Unit 4. But what we found, to our surprise, was an enormously high level of heat, excess heat, over and above that, which you can explain by the electrical process. So, of course, we ask ourselves, how shall we investigate the generation of heat in the system? What is what is the nature of the topological functions? I hope you can read that. I thought it would be useful to go through our way of thinking. We are looking for the rate of excess enthalpy generation, but of course the same thing will be true for the rate of Newton generation, turbine generation, extra generation, anything like that. I'm just considering the state vector for the generation of heat. And this will be some product of the factors which determine the nature of the material will form, the alloy composition, the processing variable, the nature of the material solution composition, factor that out as a function of 0. And if this we are unsuccessful, if we cannot get a successful material, I'm running down. Shall I shout? No, we're back on. Okay. You should have feedback now. Okay. I claim an extra minute for this, Mike. Right, so we have to get that straight, and that, of course, has been a major battle. And then, of course, if we look at it in a naive way, a simple way, we would say there will be another function, which will be a function of the cell potential and the temperature. That is the simple way of looking at it. Now, let us just get rid of this view graph and say, let us assume that we have got a satisfactory electrode material, and that, of course, is a huge assumption. Then we finish up with the simplification, but bearing in mind what I've just told you about the nature of the system, we would say that it's not just a function of the cell potential and the temperature, but also the galvanic potential difference, either within the system or between the system and the liquid, the composition, the ratio of deuterium to palladium, and we have to take into account that there might be phase changes in the system. So that is the simplification. Now that in itself is also not a sufficient description, because the actual situation is more complicated than that. The function we are dealing with includes all these terms I've put down. It, of course, also includes the pressure of deuterium. And when we start talking about the compression in the lattice, we have to factor out the hydrostatic compression. And here we have to take note that there will be an effect of shear and of straightforward compression, which would allow us to take into effect the ghostly factors, which I don't think will normally be very significant, but since we have a strong presence of scientists here from Russia, for the former Soviet Union, I will say that under extreme conditions, in fractal fusion, of course, this will become part and parcel of the overall description. And fractal fusion goes back, as so many things in the whole field of cold fusion go back to the work of Percy Bridgman in 1934, who found that chemical and physical systems behave in an anomalous way under intensive shear and compression, a subject which became known as a structure-breaking energy release, and which was well hidden from the scientific community, especially within the Soviet Union. And I hope that our colleagues from Russia will inform us to what extent factor fusion was in fact part and parcel of the structure of the energy release program in the Soviet Union. Well, having said that, let us also note that as electrochemists, of course, we could combine some of these factors, and we are interested in the electrochemical potential of the species in the lattice, which in a normal way will decompose into the chemical potential, the galvanic potential of the term, and that is very significant because we can decompose the galvanic potential into the Volta potential, which is thermodynamically well defined, and the surface potential term, which is not well defined. And this surface potential is very important, and I believe that Giuliano Caparata will give some presentation of the effect of changes in the composition, the change in the surface potential, which he will couch in the terms of the ponderomotive force exerted at the interface. But for those of you who are electrochemists or on the chemical side, we point out that what he's really talking about is the change in the surface potential. So that is the simplification which we will impose on the system. Now, the problem is actually, so we are really faced with a rather complicated situation here. We have a lot of factors, but we can only, on principle, change the cell potential and the cell temperature. Notice that the fact that we have such a complicated structure persuaded us that we should not use isothermal calorimetry because we want to leave that variable free. People say that you should isothermal calorimetry, we find that rather restrictive. Now, when you have such a complicated situation, there are people here who know about control theory, then you know that you can get more information from the system by looking at the hidden variables, the Yakimov system approach to the state vector, to allow here to take into account that these variables can change with time and to include the time dependence in the overall description. That's the Yakimov description. Of course, when we have phase changes, we would expect to see chaos. So just to persuade you that this is a sensible approach, let me show you that we do in fact get chaos under some conditions. If we do an experiment on palladium, this happens to be palladium rhodium, which shows these effects most significantly, and we monitor the cell temperature and the cell potential in parentheses here as a function of time. These are the superimposed calibration pulses. Then we reach a certain temperature at which the system shows either regular or irregular oscillations, and it shows regular or irregular oscillations in the cell potential as well as the cell temperature. And if you blow that up, you can see that to some extent there is a correlation between the cell temperature and the cell potential. So we are dealing with a strange attractor. We may be dealing with two strange attractors, and we of course have to find out the relationship between these strange attractors, or we may be dealing with a single strange attractor. So we know that we have to include the time dependence in this description. It's sensible to include the time dependence in this description, and we can ask ourselves, why do we get these oscillations? And I shall use this overhead again later. The answer is that, one possible answer is that the dissolution of helium or hydrogen in palladium is exothermic, but if we increase the loading ratio, then we would predict that at above a certain loading ratio, the dissolution becomes endothermic. Now this is a very important point to our design, the protocol which is designed into our experiments. And of course, as Mike will no doubt say later, other people will say as well, emphasize that you get excess energy generation when you get high loading ratios. So this transition here, which may be simply a consequence of the change in the entropy of dissolution, or may actually involve the formation of a third phase, you have to go through that at a sufficient speed in order to achieve the endothermic regime. And you see immediately that the outcome of your experiment will depend on the protocol, experimental protocol you adopt. All right, so we see that we have to deal with, sorry, this is not the one, we have to deal with the time-dependent system, and we see chaos, and we have to ensure that we can push the system through sufficiently rapidly through the exo-endothermic transition to ensure that we can achieve high loading and high temperature. I'll come back to that point in due course. Now, apart from these oscillations which you see at that transition point, let me show this to you again, there are no oscillations, especially there are no oscillations in the cell potential. Stein and I do not follow the electronic mail, but from time to time, people make various statements that there are oscillations in the cell potential and we do not take them into account. This, I must tell you, is complete nonsense. We do look, of course, since we carry out a very large number of experiments, we do normally only measure our cell potential at rather long intervals, about 300 seconds. But we do monitor all the oscillations. This is the day before boiling of a blank cell. Here's the cell potential 0, so there are no oscillations. And if you go further on with this experiment, you can actually have a look at what happens when the cell is boiling. For you might be interested, this is on statements about this have been on electronic mail. This is when the cell is boiling. Here's the cell potential. Now that's on 10 milliseconds per second. The other ones, I think it was on 0.1 milliseconds per centimeter scale. This is 10 milliseconds per centimeter scale. The oscillations are quite negligible to the power input. It's a nonsense. I think you can get oscillations if you do the experiment badly, but you do not normally get oscillations if you use a proper harmonic study. All right, so this is the conventional view, the Lyapunov view of what we have to take into account. But even this description is inadequate, because of course we know that once we look for hidden variables, that we will have to take into account in the actual situation the spatial dependence as well. We will not only have the time dependence of the variables, we will certainly have the spatial dependence of the variables. Now, some of these will normally not be important, but the spatial dependence of the loading will certainly be important. We can set up experiments where there is a spatial dependence of the loading. And if, of course, the Tyvanian potential difference in the lattice is important, then the cross terms, the migration terms, in composition, in the gradient, in the electrical potential will also be important. And equally, the even higher order differentials will be important. So this is the problem which confronts us, and this is the main reason why we believe that isothermal calorimetry is an unduly restrictive approach. Anyway, we don't use it, and this is the reason we don't use it. Well, how do we set about it? This is really a piece of history. You all know the type of calorimeter we use with the Dewar vessel circle at the top, so that heat transfer in the system is controlled by radiation across the base, and the whole system becomes insensitive to the level of liquid in the thermostat or level of liquid in the calorimeter. And we build a model. And the model, of course, is based on the usual black box approach. We have the heat flows into the system, electric energy in, calibration in, the heat flows out of the system, radiation, evaporation, and gas coming out of it, and here's the heat flow makeup. And we have to express that in a normal way, the model, by writing down the differential equation for the system. Well, we do that. This rate of change of enthalpy, content of the calorimeter, enthalpy input due to electrolysis, excess enthalpy generation, calibration parts, notice the square parts, not always, but mainly it's the square parts. So this is a heavy-side shift function. Here's the enthalpy removal of gas stream, here's the radiative contribution, radiation to surroundings. Now, we have to ask ourselves, how would we approach getting the information from the system? Well, one possibility is to say, let's apply the steady state approximation. So this is zero, this is familiar in kinetics. One can sometimes do this. And last year, we talked about another approach, which was to measure the lower bound heat transfer coefficient, to say, well, let's keep everything in. Let's just say this is zero, and let's evaluate the heat transfer coefficient from this equation, point by point, and see what it comes out at. And for blank experiments, you find that this turns out to be the true heat transfer coefficient. But if you do the palladium deuterium or palladium alloy deuterium D2O system, then you find that this is always less than the true heat transfer coefficient. And moreover, the time dependence of this heat transfer coefficient shows you that progressively you build up an excess enthalpy term. It's a lower bound, because of course if you set this equation, if you evaluate this coefficient from this equation, putting this in at zero, then you will get the minimum value of this heat transfer coefficient. And you can have such a high rate of generation of heat that this actually becomes negative. Well, in the normal course of events, you will of course look at that as we did in the early years, and we look at this in the early years, and then you would ask yourself the question, can I do something about this with linear regression? Can I apply multilinear regression? Or in the most sophisticated way, can we apply non-linear regression? Now, because we were under such intense pressure, we omitted most of these intermediate steps, and we went straight away from the steady state approximation and the lower bound of the heat transfer coefficient to applying non-linear regression. And we actually fitted the numerical integral of this equation, the function equation, to experimental data sets. This is the approach we did. Let me just explain to you very briefly why we took that particular approach. The reason is that with the particular timing sense which we used, we found that our main experiments are with about a 300-second time interval, that we push into the region where our interpretation would be affected by a Shannon limit, that it's not a sufficiently fine mesh, in fact, to apply, to treat the experimental data directly. So it makes sense to take a somewhat roundabout route to this and say, okay, well, I'm not limited by Shannon limit. If I integrate the differential equation, that gives me just the temperature as a function of time, and then we can fit the determined numerical temperature as a function of time with the differential equation. Right, so, well, this is the typical sort of data we have. We've got the temperature time curve, and we've got the self-temperature time curve. Notice the magnitude of these fluctuations, which is really bubble generation, very good scale here. You take it all into account. And you can do a point-by-point evaluation, and you can do it with a steady-state approximation, or you can fit the numerical interval. And we did it quite well in 1989 with this. And in the end, of course, you have to say, if I get my values of the parameters, can I, with my derived values of the parameters, can I observe my curve? And you can. However, I must tell you, one has to be honest, that really this was, there were two points to be made about the applicability of nonlinear regression. The first point is that we have not been able to make it user-friendly. It's a rather tedious iterative procedure. So you can only apply this to a rather restricted data set. And the second point is it really was a case of overkill. You don't have to go to such elaboration. And indeed, our standard approach these days is to apply linear regression. Just straightforward, common about linear regression. But we do have our own way of doing that, which I just like to point out to you, which I'm not aware has ever been used anywhere in the physical sciences. We have our differential equation, and what we do is we integrate all the terms in the differential equation. Rather than to predict the interval of the differential equation, those of you who are chemists know that the standard technique in chemistry, when you have a differential equation, as you have in reaction kinetics, is to fit the integrated differential equation. That is often a big sweat, but you don't need to do that. You can integrate all the terms individually, and then you can fit the integral, the integrated terms, to a linear equation. And here you have the enthalpy input, the calibration pulse, the evaporative heat term, divided by this temperature function. On the right-hand side, you have again the temperature function, and you have the water equivalent of the calorimeter. And this is a straightforward y equals mx plus c type equation. It's a linear equation, and it is perfectly adequate to do the analysis. And you don't need to run your calibration pulse forever. You can just take a suitable section of the data set, and you can say, do I get a linear regression? And indeed you do. Correlation coefficient in excess of 5 nines. Here's the x function. The intercept here, of course, a very big scale gives you the heat transfer coefficient. The slope gives you the water equivalent of the calorimeter. So you have some confidence that you have obtained the correct value. So this is really a set simplification. We use linear regression. But there's another side to this. We do this in two steps. First of all, we look for the heat transfer coefficient on the assumption that there is no excess enthalpy in the system, and we can use a modified approach, saying there is excess enthalpy in the system. So if we say there is no excess enthalpy in the system, and calibrate the system, we can, if we do this on the right side, we get a value of the heat transfer coefficient based on the assumption that there is no excess enthalpy generation in the system. However, we can use the calibration pulse and repeat the process and include the excess enthalpy, the calibration pulse in the equation, and then we get the actual heat transfer coefficient, which takes account of the possibility that there is no excess, that there is excess enthalpy generation in the system. So the first procedure gives us the precision of the measurement. The second procedure gives us the accuracy. Of course, what we are confronted with, I'm sorry to labor this point, but it's very important to understand the instrument we're dealing with. We are dealing with a very familiar problem in the physical sciences, or any science in fact, that what we want is to get a precise and accurate measurement. If we were looking for the center of a circle, we want a precise and accurate measurement. It is not sufficient to have a precise measurement, because we may be way off beam, and that will be the situation, of course, if there was excess enthalpy, spurious excess enthalpy, such as the reduction of oxygen at the cathode. And if we have an accurate measurement, but it's imprecise, we have this situation. So we're looking for precision and accuracy. And the question is, what will we in fact find? Well, for blind experiments, we do in fact, this was already presented last year, we do in fact find that the precision is very high, about 1 part in 10 to the 4. The accuracy is about 1 part in 10 to the 3. This is an enormous scale here of the heat transfer coefficient. And the precise value is about 1 sigma of the accurate value. So you might not think that this is significant, but the accurate value is always slightly above the precise value. And that tells us that there is indeed a small, for black experiment, a small parasitic excess generation of enthalpy. It's of the order of 1 milliwatt. But this calibration of the system does in fact gives us immediately an estimate of any such parasitic terms. So why are we interested in this? Well, we're interested in simplifying the experiment, raising the statistical significance, finding the precision, 1 part in 10 to the 4, finding the accuracy, 1 part in 10 to the 3, and we do this because we reprocess all the old data sets. Now let me just, because we are subjected to a continual barrage of criticism, let me just put this interim statement here. There are no oscillations in the cell voltage. The rate of reduction of oxygen at the cathodes is individually small, and the measurements are precise and accurate. Now, those people who wish to criticize us, of course, are very welcome to criticize us, but I would point out to them that they should not invoke miracles to explain away the effects which we have observed. We are accused of invoking miracles because we say there has to be a nuclear process, but if we are wrong, let us be shown to be wrong, please don't base the argument on these totally erroneous statements. All right. How am I doing for time? Oh my God. Okay. Well, let me just cut out this and just tell you where we did in fact end here. You all know that we had about 20 watts per cubic centimeter in March 1989, 100 watts per cubic centimeter in October 1989, about a kilowatt per cubic centimeter in June 1990, and about 4 kilowatts per cubic centimeter in the summer of 1992. Now, our search in this was dictated very much by observation for looking for high rates of enthalpy generation was directed by the fact that we had seen bursts. This is the cell temperature, raw data, increases in the cell temperature, increases in the cell voltage, marked that we could achieve marked increases in the performance of the system, and although this was very inefficient in energy terms, we did achieve about 10 times more energy out of this state than in the base, than the energy put in. So our search at that stage was focused very hard on the question of whether we could achieve high rates of energy production at high temperature by crashing the system through an exo-endothermic transition and driving it to high temperature. Of course, if this solution becomes endothermic at high temperature, then by the Chapariot's principle, we increase the load still further by increasing the temperature. So you see that, in fact, the protocol for the experiment determines its outcome. And this was represented last year in Nagoya, a situation when the cell can be driven up towards boiling. And we presented those data also in Physics Letters A this year in somewhat more detail. And the outcome was that in a limited period around here, you can drive the system to generate kilowatts per cubic centimeter, but then eventually when the cell is got dry, the cell remains hot at high temperature. And that phenomenon, here, this 3 hours, that phenomenon is becoming known as heat after death. The cell is dead, but it stays hot. And Starry Collins will give you a presentation of the analysis of some of these experiments. Let me just ahead of that time point out that, of course, what we are doing here, when we are looking for heat after death, is we're analyzing the cooling curve of the system. And analyzing cooling curves is just about the most simple form of calorimetry we can do. Why is it so simple? The reason is that we knock all the terms out. We're just left with the change in the water equivalent, the time equivalent, water equivalent of the calorimeter, and if there's no heat term in it, and the radiation to the surrounding water mass, and you can integrate that actually completely and get the equation for the system. If there is an generation of excess entropy in the system, then this will appear on the right-hand side, but you can do, it will appear on the right-hand side in terms of this term, but of course you can do details on the balance on the system, and Stan Pons will show you that. So in a sense, I want to finish with this because in our view, measuring the cooling curves after a system has been driven to the extremes of multiple generation. It's just about the most simple experiment you can carry out, and the analysis, of course, you can do with equal precision and accuracy, so that will follow regularly. Thank you.
Two technical questions. One is, in your non-linear regression analysis, your linear regression analysis, I noticed that you use Stefan's law, that's the temperature difference to the fourth power, which means you're assuming 100% radiation and no conduction. But in your 1989 paper, that March, April 89, you used Newton's law of cooling, which means it's 100% conduction and no radiation. So which of these two is correct?
Well, the point is that the cells which we used in the paper running up to the full paper in 1989, preliminary paper in the paper in 1989, were not silvered in the top portion. Consequently, there was a larger conductive contribution. That is certainly true. Now, in fact, in the full paper, we already decided to use Stefan's law, and we showed that if you neglect the conductive contribution, you get an underestimate of the excess entropy return. And our policy throughout has been to use those sets of assumptions which give us a lower bound for the excess entropy return. So the answer to that is, in fact, for the 1989 paper, there is a conductive contribution to the system, but we have done analysis so as to limit that, to limit the effects of that, to get an underestimate of the excess entropy return. The cells we use now are really 99.9% radiation, because in fact the heat transfer coefficient is what you get from the Stefan-Boltzmann coefficient of the radiant surface area. So it is pretty well nearly all radiation.
I think that's slightly controversial, because in the paper that Fritz Will wrote with General Electric, they said it's a mixture of conduction and radiation. But my second question was about pressure, where you talked about pressure on deuterium, because the problem, you know, is that when you take deuterium gas and you put it into palladium, instead of going closer together, it goes further apart. But in your 1989 paper, you said the pressure was 10 to the 26 atmospheres on the deuterium, and that's unprecedented. Do you still believe this?
In the preliminary paper we published in 1989, we tried to take a shortcut explanation, and we've paid dearly, especially at your hands, for having made that shortcut. I have given you the formulation. The correct formulation is neither in terms of activity nor in terms of pressure. The correct formulation is in terms of electrochemical potential. And of course, every electrochemist in this room would have told you that in March 1989, that that is the correct formulation. And this is something which we all have been aware of forever.
So the PD is 10 to the 26 in the formula you showed today?
No, not at all. There are various approaches to this. If you do the pressure experiment like Baranovsky does, you have to express it in terms of the fugacity of the gas. If you do it in terms of electrochemistry, you have to do it's much more. Baranovsky doesn't like this, but in fact it's much more straightforward to do it electrochemically and to express this problem in terms of the electrode potential, which you can measure. And Stan will show you that you can achieve extremely negative potentials in these systems, far higher fugacities, if you like. You want to talk about fugacities, you can't really. Fugacity is something that's simply to the gas. If you want to talk about activities, you can achieve much higher activities electrochemically than you could ever do by compression of the gas. That remains true. You just cannot achieve such compressions in the gas phase.
I guess this was a grand paper, Martin, and therefore I really want to make one very general comment on it, which applies to the whole subject. your general introduction and how we all think and how we all is thought, you talk about D+, and this then gives rise to all the trouble with the blue barrier and so on and so on, and everyone so well. And in recent times, I've been looking at the structure of hydrogen and deuterium in metals. And now, if you look at the actual amounts of D+ in palladium, you find that they are relatively small. Most of the D in palladium is not D+, but it's atomic. And most of it is absorbed in imperfections in crystals. So I think that the entire idea of looking at R D goes in D+ isn't correct. I think that makes a great deal of difference. One thing, it removes the blue barrier.
I think this is an important point, but I would like to disagree with you. I think that, as I will show, the experiments of Alfred Koenig were extremely clear on this issue. These experiments became ignored. They were then resurrected because Carl Wagner did some measurements on this. But I think the implication, the effective charge ratio, which has been put on from electromigration experiments, is untenable. I think that it's just a straight mistake. I think it is D+ under all conditions in the lattice, but it can be partially screened, so that if you do short time scale experiments, scattering experiments, it will behave as though it was screened. But I don't think it is so. It is no more sensible to ascribe a partial charge to deuterium in the lattice than to try to explain away the bifalkenhagen or Wien effects for electrolyte solution in terms of partial charges. We know that it is not so. We look at the dynamics. There's been a total confusion in the literature of this point, but this will take about a week to discuss.
My guess is that Professor Oriani has something to say on this point.
Yes, I'd like to make a remark about this point, that electromigration experiments have to be understood in terms of kinetics. There is a cross effect between the motion of electrons and electron holes in metal and the motion of the dissolved species. You've got what is called a wind effect, as well as the normal electrostatic field effect. And we measured some of these too, and it's impossible at the present stage of the theory to deduce anything but the ionicity of the dissolved species from electromigration effect.
Well, I agree with you up to a point, but just bear in mind that the wind effect would derive from neutrons with an anode, not a cathode. So Koenig's experiments, I think, are totally clear on this.
One has both electron hole momentum transfer to the species as well as electron momentum transfer to the species. And which of these is predominant for the wind effect is a very difficult point.
Yes, but Richard, if you look at that, you find that the most extraordinary conclusions have been derived by looking, if you look at Parle's paper, for example, great man though he is, was, I don't know, is he still alive? Giuliano Parle, is he still alive? Is he great man though he is? The conclusions are untenable, and I think the only safe assumption you can, I don't mind, you can ascribe a partial charge to the deuterium in the lattice, you will still come up with the most horrendous effect on the potential energy of the system in an applied electromagnetic field in the lattice. That is the point. You can screen if you like a little, but I do believe that you're dealing with unscreened neutrons in the lattice.
Okay, that belief is all right, you can have that, but you cannot deduce that from the electromigration effect. You can have a perfectly neutral species and still move the electric field because momentum transfer.
Not, I submit, not if the mobility fits the Nash-Einstein relationship. Then you would really have to invoke several variables.
In the interests of keeping on the schedule, I must declare this discussion at a close, and move on to the second paper in this morning plenary session, which will be presented by Professor Gotzi. The paper is entitled Excess Heat and Nuclear Product Measurements in Cold Fusion Electrochemical Cells.
Mr. Chairman, I would like to thank the organizing committee, to assign to our group, to Leonard Lechley, and I hope to show you today and tomorrow by my colleague Guido Gigi some interesting aspects of cold fusion. Just a few sentences to present our team. This is composed by two groups. One is composed by physical chemists, the other by nuclear physicists. All the research activity is at the Department of Chemistry of the University of La Sapienza in Rome. In preparing this talk, I decided to divide this talk into parts. The first part is strictly related to cold fusion aspects, heat excess, even for tritium neutrons, and the second part to detail confinement in spotlight. In my opinion, this is a general aspect of the behavior of the hydrogen and the isotopes in the metal, which is not strictly correlated to cold fusion experiments. To save time, I decided to cut this part, but I am free. I have your disposal for any comments you wish. I just present the single cell flow chart, which is for all the cells in our multi-cell systems. We have the electrochemical cells, which is connected to a catalytic recombiner for the gases produced under electrolysis, and after a separator for deuterium, which allow us to cut the most part of deuterium for successful even for mass spectrometric determination. This experiment started on May 31, and its length was about 1,000, more than 1,000 hours. And in this case, we used only 6 cells, which we made tests, simultaneous tests for helium-4 and deuterium. In this table, we have the cells we used and the nature of the cathode we used. The cell number 1 is a blank cell with platinum cathode in water. And cell 4 is a special cell which we dedicated to make confinement experiments. I will show you after. In the cell table we show some difference between the preparation of the cathode and the gas line materials. Tomorrow morning, my colleague Guido Gigi will show you that using stainless steel or nylon, from the point of view of the air contamination, there is no significant difference. Okay. This plots show on the left side the input power and on the right side the heat power excess. This is cell number 2, and we have an heat excess, heat power excess of a maximum about 9-10 watts. This corresponds to about 100 watt per cubic centimeter. If we superimpose the helium-4 pattern, we have that we measure helium-4 about the maximum value we measured was about 20 ppb, and our background is in general at the level of some ppb. This is cell number 4. This cell is constituted by a candle of a 6 mm diameter, and in this cell we didn't find any significant excess heat. I have to remember that in our calorimetric measurement, the error is within 10%, and the detection limit of excessive power is less than 1 watt. The helium-4, the helium-4 scale is different. In this cell, we observe that this trend of the helium-4. The helium-4 increases slowly and reaching at about 300 ppb. This is another cell number 8, in which we obtain excess power at about 11-12 watts, and the helium-4 is there is a pattern of helium-4 which has a slight time coincidence with excess heat. But what is very significant is the behavior of cell 10. In this cell, we obtain about 20 watt of excess heat on about 30 watt of input power. And the helium-4 we detected is of the same, is not considered from the point of view of time. There is no strict time correlation, but we have excessive helium, excessive helium, excessive helium. To compare the calorimetric measurement and the helium-4 data, it's necessary to make mass balance in our cells. So, in our cell we have nitrogen coming from liquid nitrogen, which acts as a carrier gas, and the cells produce oxygen and deuterium by electrolysis, and eventually helium-4. So, the atomic helium-4 fraction in the cell is given by this relation. B is related to the flux of carrier gas, and eta is the yield of recombination of a catalytic recombinator. If we suppose to have a short time interval in which we have a constant current and an excess power constant, we have this simple relation in which we can estimate the atomic helium-4 fraction for 1 watt of excess heat. But to calculate the excess power from helium-4 data, it's necessary to evaluate the quantity which we named minimum sampling time, which is the time necessary at our total gas flux to fill our sampling volume. This time depends on the recombination yield of the catalytic recombinator and from the carrier gas flux, and also by the electrolysis current. This plot, I show the minimum sampling time versus the current. It's easy to see that if the heat of recombination is quite at 100%. The minimum sampling time is independent of the current, as expected. And the expected helium-4 for 1 watt of excess heat in the same way as elevated heat of recombination does not depend by the current. So, through this consideration, we can compare in the same scale the excess heat by calorimetry and excess heat by helium-4. In the case of the cell 4, we have a very low value of excess heat, and the excess heat coming from the helium-4 data is higher, but of the same order of magnitude. After this line, we make some manipulation on the cell to check some aspect of tightness of the cell toward a contamination. So this is a prudential line. Tomorrow morning my colleague will explain in details this point. But coming back to the cell 10, we observe that excess heat and from calorimetry and excess heat coming from helium-4 is practically the same order of magnitude, but shift on time. First excess heat after helium-4, excess heat after helium-4. The integrated excess heat by calorimetry and from helium-4 show that the error on the calorimetry, I repeat, is about 10%. So there are practically the same error bar of the helium-4 data. And as you can see, there is practically a ratio 1-to-1 from heat excess coming from helium-4 and excess heat coming from calorimetry. I would like to draw your attention to the fact that the helium-4 data, excess heat from helium-4, is higher than calorimetry. Because we were measuring the helium-4 concentration higher than the ground measured before starting with the electrolysis, at half about the experiment we posed the question, was helium-4 found really coming from cold fusion? How to check a possible air contamination? We decided to make the mass spectrometric determination of helium 20. Sometimes we found helium in a ratio with helium-4, which was at least 1 order of magnitude of the ratio present in the area. The helium-4, helium 20 never is less than 0.3. Never we found this value. The value which we found was an order of magnitude greater than this value. Tomorrow morning, we will give you more details on spectrometric measurements of helium-4. Go to tritium. To avoid air contamination, we made tritium measurements only in a recombined gas, not in solution. The equation to estimate the electrolytic enrichment is one, and we define this quantity Q, which is given by the ratio by the tritium atomic fraction in gas phase and the initial atomic fraction in solution. So we have this equation, which is very similar to the equation found in literature, and this is put in a different form because we correctly have the dependence of the heating water consuming, which is a function of the current, because in our experiment current is not constant. It can be shown that the quantity Q, in the case of no-tritium production, has to be always less than 1. If Q is 1, this gives an absurd, because we had that this ratio from electrochemical enrichment factor and the ratio between the vapor pressure in water and the distilled water would be less than 1. This is possible. So if Q greater than 1 was fine, this strongly implies excess of tritium over the electrolytic enrichment. This is just a three-dimensional graph to show you this fact. If we work for absolute to a very, very low electrolytic separation factor, I remember that in palladium we have about 2 as electrolytic separation factor. This implies a Q being greater than 1. This is possible. The experimental results are shown for blank cell and the other cell. For blank cell, we use in calculating the theoretical equation the same separation factor for platinum, but this is not correct. The solid blue line is the theoretical, the expected trend of the Q quantity as a function of EV water consuming. And as you can see, there are some points in which we have a Q value greater than 1. On the right scale, there is the integrated tritium atom produced during the experiment. Also for the other cells, also in this case we have some points which are greater than 1. Go to the neutrons. As I showed last year in Nagoya, we have a large neutron counter with 60 helium-3 tubes, which are divided in 12 groups, 12 separate counters, which are separated electronics. And in this detector, there are the tubes containing 10 cells. This allows to us to have a certain degree of spatial resolution to have information of the source of neutrons. But we didn't find any significant excess of neutron. This is, for simplicity, I reported only 6 groups of the neutron counter. This is the background value. This is the experimental value. As you can see, for example, in channel 12, we have some spike. But due to the characteristic, the feature of the neutron counter, also the closest neutron counter group would have to count the same spike. If we check this path, we observe, because we have the storage system of each path, the data of each path shape, we observe that in this case we have some sparks in the tube. This is so an artifact. Going to the conclusions of this first part, we have to conclude that the combined detection of the helium-4 and of a nominal mass 20 attributable to neon 20 to both a conditioning correlated
to correlate helium-4 and heat excess. The high sensitivity mass spectrometer in an open electrochemical system displays all the difficulties to demonstrate the nuclear nature of the cold fusion through the helium-4 channel. But the overall picture emerging from the present and tomorrow morning results does not show a clear-cut evidence of air contamination, at least as unique source of helium-4, and particularly in one cell 10, we observe that integrated heat excess from both the calorimetry and the helium-4 show a ratio close to 1. And excess heat power from calorimetry is of the same order of magnitude of excess heat power calculated from helium-4 data, even if there is not a strict time correlation between them. There is a clear evidence of excess heat followed by helium-4 sharp increase. But in general, if helium-4 were really produced in the bulk, how long would be the time for helium-4 to reach the surface? This time could rapidly change due to a rapid generation of the fracture induced by deuterium palladium. Further, the excess heat power values found are consistent with our previous findings and the literature data. Any evidence of excess of neutrons above the ground, and some just significant excess of tritium. Now I come to go to the second part of my talk. This part is the deuterium confinement in palladium. In 1990, we published a paper on Junior Material Science Letter entitled on the possibility for local Earth circulation of deuterium palladium, in which we consider the electronic ionic transport process in the mixed conductor, and on the basis of the well-known Wagner equation, we put some ideas on the way to confine deuterium in the metals, in special case in palladium. What is our point of view? Why under electrolysis we can increase the DPD ratio over the value expected for PD2, which is in electrolysis very close to 1 atmosphere. Literature and our experience on high temperature oxidation of metals under electric field applied to the ground oxide show that the oxide growth can be retarded or accelerated depending on the value and scene of the electric field. Here, electron migration works because oxide is a mixed conductor. Is it realistic to apply the same constant in the palladium cathode? Our answer is yes, if the deuterium transport number is different from 0. In this case, for example, if we have a blocking interface, palladium, which is loaded by deuterium, and deuterium is produced interface by the electrochemical charge transfer, if there is not any field inside the electrode, we have that the gradient of the chemical potential would be directed in this way. And when the chemical potential is equal, we have no flux of into palladium. But we know, this is an experimental evidence, that this is the loading of palladium continue at value which is not compatible with thermodynamic equilibrium. we plan to make an experiment to demonstrate these effects. And we modify one of our electrochemical cells by making a cathode with a blocking interface made by gold and a third electrode spot welded on the surface of the palladium. This is a non-compound, non-electrolytic. And we have the anode. And we have two power supply. The first power supply gives the electrolysis, and the second power supply is supplies the confinement current and apply a current between the cathode and the external electrode welded on the surface. We have the gas which escapes from the cell, goes in the catalytic recombinator and in the palladium trap, and the gas is sampled for mass spectrometry, mass spectrometric analysis. This is an overview of our results. On the left scale, we have the concentration expressed in part per billion of deuterium in our cylinder, sampling cylinder, and DPD in our trap. Our trap is a palladium sponge trap. This is not the electrode, this is palladium sponge trap. And taking into account this kind of relation, which is calculated by neutral data, we can replot the plot before in this way. On the left scale, we have the partial pressure of deuterium, and on the right scale, we have the deuterium content in the palladium sponge trap. As you can see, the pressure measured is the pressure in equilibrium with palladium sponge loaded at this value deuterium. This is an image of what happens in cathode. This is not the true value of the loading of the cathode. This is the proportion, this is an image of what happens in the cathode. So we can go into the details of a part of the graph I showed before. On the left scale, we have the cell voltage. I mean the potential difference between cathode and anode. And on the right scale, the current, confinement current, and the electrolysis current. In this region, we are at zero confinement current value, and at this value of the electrolysis current, as expected, because we have an isothermal method, the voltage is constant. At this time, we apply 4 amperes in confinement current. As expected, there is a voltage drop due to the fact that the current crosses the electric resistance. This is a way to measure the real time the electric resistance. But what is very interesting is the fact that all this is constant. The electrolysis current is constant. We have a change of the potential difference of the cell. At this point, we change the electrolysis current, but maintaining constant the confinement current. As expected, there is an increase of the voltage of the cell, but after we show you a magnification of the structure, there is another tract in which the voltage of the cell continues to decrease. These two situations are different because we have the same confinement current, but different level of the deuterium concentration at electrolyte This is a magnification of this product. At this point, we have the current density 400 million, the electrolysis current 400 million first, and at this point, the confinement current goes first from 0 to 4 amperes. At this point, the confinement current is still constant, but the electrolysis current goes from 400 million to 200 million. And on the left scale, we have the deuterium concentration in gas phase. As you can see, this value is in the graph, less than 20 G. This is the same graph I showed before, but on the same scale, time scale, we plot the current, the electrolysis current, the confinement current, but on the left scale, now there is the dB ratio in palladium trouble. As you can see, the integral of these two peaks are very different. The ratio between them is more than 2. This means that due to confinement current, we loaded at higher value the palladium cathode. And there is another interesting thing. At 246 milliamperes per centimeter, the system did not release deuterium. But at 62 milliamperes per centimeter, we have a release of deuterium. Unfortunately, we have not other points in this way, but we can confine the value of the threshold of the current density, because this value, since 5 years, is very often reported in literature too, and which people find a threshold of the current density at which heat excess or nuclear phenomena occurs. This graph is very important. The magnified view of the two situations. This is the first situation I showed before, and as you can see, there is a practical linear decrease, but in effect this is an increase because this depends on the scene, on the way we are measuring the voltage of the cell. And this corresponds to an electrolysis current level of 400 milliampere. This is the same situation from the point of view of the confinement current, because we have 4,000 milliampere, 4,000 milliamperes also in this case, but the current density is 100. The electrolysis current density is 100 milliampere. As you can see, there is a lower slope of this curve. So, what we mean for confinement. In a stationary state, which we don't think to a moving boundary of deuterium or polonium, we can show that the ratio of the concentration of deuterium at the electrolyte interface L, and at certain point in the inside the electrode depend from this quantity, which delta V is the potential difference in the layer in which is concentrated the electric field. But as Martin said before, depends on the effective deuterium charge. Delta depends. Delta gives this quantity. deuterium goes into palladium, but not with a simple diffusion process. It's a process assisted by the electric field, because when a layer of deuterium is formed, in this layer an electric field is generated by a flux of electrons which across the layer. So, in this way, inside this layer we have this trend of voltage and this trend of the chemical potential of deuterium. We can treat this data on the basis of Wagner theory. Wagner theory was used to calculate the kinetics of oxidation of metals of ionic products, and the dependence of this voltage drop from temperature is related to this quantity. But a very important conclusion is that when delta x, the thickness of the layer, become constant, equal to the radius of the cathode, we have a situation in which the voltage drop continues to grow, and this depends on the derivative of the chemical potential and the ionic transformation of deuterium. This quantity is always positive. Just to finish, I want to show you some scanning electron microscope. This is a cross-section of electron which we need confinement experiment. As you can see, there is a corona in which there is a massive effect of the nucleation of the other phase. At present time, we cannot have an analysis of this corona, but it's important to see that there is a island of nucleation, dendritic nucleation, which is typical of high concentration of deuterium and the precipitation of deuterite. So the partial conclusion of this part are starting from the well-known fact that the deuterium palladium is in a quite ionic state. We look at the PDD system as a mixed conductor that is an ionic transport different from zero. Then, if a flux of electrons crosses palladium, deuterium moves in the metal under the combined action of two gravits, chemical and electric potential. And in simple experiment, we demonstrated this effect as we showed applying a more intense current, superimposing the electrolysis current across the palladium cathode. The simultaneous mass spectrometric analysis of deuterium cell clearly showed that really we can control the deuterium confined to palladium. And the final conclusions are, nevertheless, we have work to be done. We cannot give a decisive contribution to the heat excess helium-4 key point of the cold fusion, but only quite good evidences. On the other hand, the overall picture emerging from our results goes in that direction that helium-4 channel is the dominant process in cold fusion. If the cold fusion trigger, as we believe, is a high DPD ratio, the deuterium confinement results indicate a route as to reach heat. And finally, let me to present a piece of pathological science. In 1991, Edwin Stokes published a review on fusion technology, and they reported the thermodynamic data known at that point on the scale of excess power per square centimeter with respect to the current density. The unique data which are very different from this framework were the data of Leo obtained in high temperature system. I recall that this result was obtained in molten salts. But if superimpose the results we obtained last year at the Nagoya conference this as well, and the present calorimetric data of the cell 2, 8, and 10. We go on this line. And if we plot the recent data of the flashing points, we have this point. But the data of the flashing points are in high temperature system. They claim that the KLF support of the cathode melted, and KLF melting point is above 300. Thank you very much for your kind attention.
Can you unambiguously distinguish helium-4 from molecular D2 in the metal?
From the metal, we made measurement in the gas phase, and we cut practically all the deuterium in gas phase by catalytic combination of the helium group, deuterium and oxygen, and after elimination of residual deuterium by palladium sponge trap. I showed you before that our background of deuterium is less than 1 ppb, and by our mass spectrometer it's very, very easy to separate in this condition helium-4 and deuterium. It's very, very easy. It's no problem.
Your team from Purdue, can you comment on whether you measured the gamma ray, or you had a gamma ray detector while helium-4 was coming out?
No, unfortunately, we cannot measure the gamma ray because our experimental arrangement now is constituted by a large neutron detector, and it's impossible, physically impossible for us to put around the gamma detector.
You will be doing that
probably in the next.
This morning before the break will be presented by Dr. Keiji Kunamatsu. The paper is entitled Observation of Excess Heat During Electrolysis of 1 molar LiOD in a fuel cell type closed cell.
Good morning. My name is Kunimatsu from Japan. It's my great pleasure to give my talk today for this presentation. I'm very grateful to the conference organizer to give me a chance to speak about our research activities. So my title of today's talk is observation of excess heat during electrolysis of 1 molar LiOD in a fuel cell type closed cells. What I would like to talk about is given on this list. First of all, I'll talk about something about introduction, especially from our former data presented at the Nagoya conference. Then I'll talk about some basic things about our experiments. And then I'll talk about reproduction of our excess heat against deuterium loading ratio in the region lower than 0.9. And next, I'll talk about excess heat measurement for DOPD higher than 0.9. The reason why I am separating my talk by the value of loading ratio of pure palladium itself. So then I will talk about something about discussion on the factors controlling cathode loading, and also I would like to just make a very short comment on factors controlling excess heat. And then I'll make some very brief conclusion on our research activity. So probably many of you remember this data, which we presented at the Nagoya conference last year, to give the excess heat as a function of deuterium loading ratio. So in this figure, we meant to show that excess heat is generated as a function of deuterium loading ratio from somewhere 0.83 or 0.84, and increases steadily with increasing deuterium loading ratio. So when we had this data last year, obviously it's very easy to see problems in these figures. First of all, it's very obvious that our data for the deuterium loading ratio is restricted for the region smaller than 0.9. This is our problem. And also, our accuracy for measurement of deuterium excess heat is not so good, which is given by this green line saying ±5%. So our next task after the Nagoya conference was to go into the region where the deuterium loading ratio is higher than 0.9. That's a very natural, I think, plan if we have this sort of data. And then we try to check our accuracy of measurements in the excess heat. And then, of course, we try to reproduce this sort of general tendency of excess heat generated as a function of deuterium loading ratio. So with this data, we showed that excess heat is also expressed as a function of applied current density, which is given by this figure in the bottom. So before I talk about our data to reproduce, I would like to make a very brief description about our experimental procedures. As you probably know, we are using closed electrolysis cell using partially immersed fuel cell anode. So in this configuration, we have palladium in the center of the cell, and then we have anode, which is fuel cell anode, partially submerged in the electrolyte. And then actually this fuel cell anode is surrounding the palladium cathode cylindrically. So we have deuterium gas of about 5 to 10 atmospheres in the cell. So if we electrolyze under this configuration, we have the oxidation of deuterium gas molecules to deuterons by the action of fuel cell anode. And then these two deuterons combine with two electrons from palladium cathode to give rise to D2 molecules. So if the cathode does not absorb hydrogen at all, then we have just a circulation of heavy D2 molecules. So in that case, there should be no pressure change when we switch on the electrolysis current. But because palladium absorbs a lot of deuterium into itself, eventually the pressure of the deuterium gas decreases. Then we have the equation for the overall reaction in this cell, which gives simply the description to show the absorption of deuterium gas into palladium cathode. And I should remind you, in this configuration, there is no oxygen evolution at all at anode. This is very difficult to understood for those people who are not familiar with fuel cells. But this is a very important point. And then we can calculate the deuterium loading ratio online from the pressure limits during the experiment, which is given by this simple equation, which includes the internal volume of the cell, and initial pressure of the deuterium gas, and then the actual pressure during the experiment, and gas constant, absolute temperature, and the number of moles of palladium atoms in the palladium cathode. So the actual system to measure the excess heat and DO or PD is described here by this block diagram. The essential point in our calorimetry is that we are measuring the temperature in the palladium cathode by inserting thermocouple into the top portion of the cathode. So, and we have two vessels actually. One inner vessel which contains electrolyte, and then the outer vessel to have a good heat insulation by the action of air in between two vessels. So what we do for calorimetry is to measure the temperature in the palladium cathode, and then we compare this temperature increase with the similar data observed by using nickel cathode. And then we combine the excess heat measurement with the data measured simultaneously for the deuterium loading ratio. So again, this is the data which we presented at number of conference to show the what we call calibration graph obtained by using a nickel electrode to show the relation between input power and then the cathode temperature increase. And then if we use a palladium cathode, we have these green and red points to show the deviation from the calibration graph. The data which I showed first, this one, was derived from this sort of relations. So now the reproduction. But to go to the reproduction, I must point out that when we were preparing for this conference, and then check all the data, we have found that we have two more sets of very similar data which were obtained at nearly the same time with this one. So I should say this is the second cell, and this is the first. So they are very similar, but if we plot the excess heat against the deuterium loading ratio, we have this, which is not so nice, very scattered around the x-axis. But if we plot all the data as a function of current density, we have this, which is much nicer than the data presented as a function of deuterium loading ratio. The reason probably is at that time, when we have this data, we were using electrolysis cell with a very thick Teflon helix in the cell. So the Teflon absorbs a lot of deuterium gas in, and then this gave us a very serious problem on the accuracy to estimate the deuterium loading ratio. So after this, we avoided this structure to have a very thick Teflon in the electrolysis cell. And I'll show you one more similar data with the same data, but plotted as a function of cathode overvoltage. The notion of cathode overvoltage, especially for high-voltage electrode, probably is difficult to understand for many people who are not familiar with electrochemistry. But the overvoltage is defined by the difference between the electron's chemical potential at the equilibrium potential and at the actual working state. So the overvoltage expresses the energy of electrons in the palladium cathode. So if you plot the excess heat as a function of cathode overvoltage, we have very scattered. But if we look at those data closely, those green data and red one and white one are well separated, and it looks as if they are well on the straight lines. The reason why we thought about plotting the data as a function of overvoltage is as a function of current density. The current density has nothing to do with the performance of the actual characteristics of palladium cathode. Only cathode overvoltage can give us the potential drop across the palladium solution interface, and also, as I have written down, we know the change of electrochemical potentials of electrons in the palladium cathode. And from these old data, we also know that this shows the excess heat, the change of excess heat along the time axis, which continued for nearly 30 days. And then we are showing the dWAPD at the top. But we superimpose this with the actual current applied during this period. We can see a very close correlation between the excess heat change and the current density change. Again, the current density and overvoltage is very well correlated in many ways. This is another description to show the close relation between excess heat generation and the change of cathode overvoltage for this experiment nearly 2 months. So just a general tendency to increase cathode overvoltage and then increase the excess heat during this period. So these are our old data. So I would like to show some of our new data. But before I talk about new data, I would like to talk about something about our accuracy in the excess heat measurements in the new situation. By showing the data for the light water system on palladium electrodes. So if we plot the cathode temperature change as a function of input power for the palladium electrode and nickel electrodes, because we regard the data by nickel electrode as a calibration curve. So we see a very close correlation or coincidence between nickel data and palladium data. So from these data, we try to estimate the accuracy of our excess heat measurement, which is given here. So I'm plotting the data points scattered from the straight from the calibration curve. So this 5 points show the deviation of the data on the palladium electrode from the calibration curve, which is not so bad. In this case, I would say our accuracy for the excess heat measurement is probably plus minus 0.2 watts per cc of palladium cathode. And again, this tells us not only the accuracy, but also the absence of excess heat in the light water system. If we compare the data on palladium and data at the nickel cathode, this is excess heat expressed in terms of watt per cc as a function of H over PD. So for hydrogen system, we can go to very high loading ratio, very close to 1, but up to 0.99, we see very, very little deviation from the zero line to show very, actually no excess heat for this system. So the reproduction, we tried many electrodes because we didn't know, and still we do not know the importance of palladium materials. So we purchased many purchased palladium cathode electrodes from various sources, including Imra Materials, which is our colleague company, to support us for metallurgical issues. And also, we tried the sort of Tanaka heating coal type C, which is very heavy coal watt under liquid nitrogen. Also, we tried Tanaka usual palladium electrode, which is purchased at ordinary basis. And also, we had Johnson Matthey palladium cathode from England, and also, yes, also we tried different batches from Imra Materials. So this 911 9209 and 930 means the different batches dispatched to our company at different times. So, and then green data are the data which I presented at the NAMA conference. So if you look at these data, the data points are rather scattered, but this part shows no excess heat for the light water system, and this part shows there is no excess heat evolution in the region of deuterium loading ratio below 0.8. And then after 0.8, 2 or 4, we have some appearance of excess heat. If we plot this data as a function of current density, we have this. Again, the green plots, those which we presented at the NAMA conference last year. This change of excess heat as a function of current is also do not look so systematic. But if we plot the similar data, most of the data as a function of cathode overvoltage, it looks much tiny and ordered. So we are wondering if we should consider the cathode ore voltage as a more important factor controlling the generation of excess heat. And I'm showing by this figure the relation between cathode ore voltage and current density, which is called usually Campbell line by electrochemists. So the green one, which we presented at our conference, shows very high hydrogen ore voltage compared to other various hydrogen cathode. We still do not understand why this particular hydrogen cathode gave so high, much higher cathode ore voltage than others. And if we look at these data presented as a function of cathode ore voltage, the reason why this green line, green data are showing the highest cathode ore voltage is simply because it has much higher cathode ore voltage than other hydrogen cathode. So again, this one, with this new set of data, we have still some difficulty in going beyond the loading ratio of 0.9. Although we have some data for the new electrode to show the loading ratio slightly higher than 0.9. This one, Johnson Massey, palladium, and also the new match from Imra materials. But to go further beyond these points, we have to do something on the electron surface, as it is very commonly done by the group at SRI to add something like aluminum into electrolyte. But we are not happy to have aluminum in our fuel cell system, because aluminum bites the fuel cell anode and it kills the action performance of the fuel cell anode. We had a very serious problem, so we gave up almost to add aluminum into our electrolyte. Instead, we tried to add thiourea, which is very well known by electrochemists, to increase the overvoltage for the recombination of absorbed hydrogen to give rise to hydrogen molecules, which is reported by a group of Professor Ayo in the early 1980s. So the action of thiourea is supposed to be chemical on the surface through sulfur atom, then it sits supposedly in between two hydrogens to be combined. So it poisons the chemical thiourea is supposed to poison the recombination step of two absorbed hydrogen molecules. So Professor Ayo shows if we have thiourea, the loading ratio could be significantly improved for hydrogen. So we tried this thiourea into our systems. Then I'm showing the effect of thiourea for 1 molar LIOD system. So I'm plotting the deuterium loading ratio as a function of cathode current density for pure 1 molar LIOD and 1 molar LIOD containing 0.6 millimolar thiourea. So if you look at this data, it is very easy to see the effect of thiourea to increase the deuterium loading ratio substantially in this region. So we have nearly 0.93 or 4 for the maximum deuterium loading ratio in the presence of thiourea. And similar data, actually the same data, when we plotted the same data as a function of just very similar tendency. We have these data for hydrogen, also as a function of current density. For this, we have 0.1 millimolar thiourea, and also the data taken with 0.6 millimolar thiourea. So it's very clear that for hydrogen system, we can go slightly above the loading ratio of 1 by adding 0.6 millimolar thiourea. We have never tried to add more thiourea because thiourea also is case of gas diffusion electrode, fuel cell anode, and then the action of fuel cell anode is slightly retarded in this case. So 0.6 millimolar is a typical concentration for this system. And the action of thiourea is very clearly displayed by this data showing the desorption of hydrogen from trident cathode after the current is terminated at this time 0. So, and then other function time. So for pure 1 molar LiOH, the hydrogen dissolves very quickly and then reaches the bottom. And then gives rise to the hydrogen loading ratio at the equilibrium potential. But with 0.1 millimolar thiourea, the absorption becomes slower, and then with 0.6 millimolar thiourea, the desorption from the cathode becomes very slow. It is taking nearly 2 weeks and still not reaching the final steady value with this 0.6 millimolar thiourea. So this strongly suggests that the thiourea is actually retarding or causing the recombination step of to absorb hydrogen atoms, thus inhibiting hydrogen desorption from hydrogen cathode. And I'm sure this is the reason why we have